Greetings to everyone. Welcome back. So, this is our last topic in our Unit 4. That is about, sorry, not last topic, yeah, last but not the least. Okay. So, this is about conducting polymers. So, as we have seen, polymers are generally insulators, right? So, they cannot conduct electricity. Then, how can we say about conducting polymers? So polymers which can conduct electricity are called as conducting polymers. But ordinary polymers obtained by usual methods are merely insulators. So however, some specific polymers may act as conductors. How? So the classification of conducting polymers may be classified as follows. So it is intrinsically conducting polymers and extrinsically conducting polymers. So in intrinsically conducting polymers, we have conducting polymers having conjugated pi electrons in backbone and doped conducting polymers, that is para-doping and n-doping. And in extrinsically conducting polymers, we have two types, that is conductive element filled polymers and blended conducting polymers. So now we'll discuss in detail about each and every one. So here, intrinsically conducting polymers, these polymers have a solid backbone made up of extensive conjugated system which is responsible for conductance. Okay? So in the system, inbuilt, okay, they say that as inbuilt. So it is there within that, okay, as backbone which can help in conducting electricity. So these are again of two types. First thing is conducting polymers having conjugated pi electrons in the backbone. What is meant by conjugation? Presence of alternate double bond. Okay. So if they have alternate double bonds, that is pi electrons in the backbone, then they are able to conduct electricity. Okay? So these polymers essentially contain a conjugated pi electron backbone responsible for electrical charge. Okay? So they get excited, right? You know, pi electrons of the polymer get excited, which can be further transported through the solid polymer. So overlapping of orbitals of conjugated pi electrons over the entire backbone results in the formation of valence bands as well as conduction bands which extend over the complete polymer module. So the presence of conjugated pi electrons in the polymers increases its conductivity. So example we have here pyrrole. So pyrrole can be made polypyrrole. So there are alternate double bonds you can see. That is pi electrons in the molecule, entire polymer molecule, which helps in conjugation. That is helps in conductivity. Okay. Then next is doped conducting polymers. So the conducting polymers obtained by exposing the polymer to a charge transfer agent, either in gas phase or solution, are called doped conducting polymers. Usually, in this doping technique, we use iodine tetrachloride and sodium naphthalate. Okay? So, with the use of these two, para-doping and n-doping is done, and we have this what to say, yeah, conductivity done in the polymer. Okay? And then we have advantages of intrinsically conducting polymers, that is their conductivity, ability to store a charge, then ability to undergo ion exchange, then they can absorb visible light to give colored products, then they are transparent to exposed. Then coming to extrinsically conducting polymers, we have conductive element filled polymers and blended conducting polymers. So for conductive element filled polymers, we take carbon black because it has high surface area and absorption capacity is more. So we add carbon black to the polymer in order to conduct electricity. Then blended conducting polymers, we blend the polymer with another material in order to conduct electricity. So this is about the intrinsically conducting polymers and extrinsically conducting polymers. Now coming to the applications of conducting polymers. So we have these conducting polymers as coatings. Okay, they can be used as coatings, which build up static charge in insulators. So then it absorbs the harmful radiations and healthy polymer. So polymerization of conducting plastics used in circuit boards. Then these are used as sensors, that is polypherols can detect NO2 and ammonia gases by changing its conductivity. Then biosensors, okay, they can be used for glucose sensor. Okay. And then we have biocompatible polymers, that is artificial nerves and brain cells can be used. Okay. Then batteries. So we have all batteries made up of toxic metals and all. So if we use conducting polymers instead of those, then it will be of lightweight and rechargeable and non-toxic. So example, we use polypyrrolithium and polyaniline lithium. Then these can be used as displays, that is flat panels, low lifetime and long switching times. So we can know that mobile gives two different types of lights, that is while charging and while discharging. Okay, similarly, these displays are done by those conducting polymers. Then these can be used also as adhesives. Right. So these are the applications of conducting polymers. Now we'll go for another topic, that is water. So water, as you know, is nature's most wonderful, abundant, useful compound used by the human beings and all, right? Whether it is non-living, human, everything we use water. Right? Then occurrence of water, that is 75%. Matter on Earth's surface consists of water. Then body of human being 60%. Plants, fruits, vegetables 90 to 95%. Right? Then sources of water are surface waters and underground waters. So these you know. Then coming to the causes of hardness. What is hardness? The property of water which does not get lather with soap is called as hardness. Okay? So this hardness is of water is due to presence of certain salts like bicarbonate, sulfates, fluorides of calcium, magnesium, and few other heavy metal dissolved salts. Okay? So a sample of hard water when treated with soap does not produce lather, but on the other hand forms a white scum or precipitate. So what is that white scum or precipitate formed are of calcium stearate and magnesium stearate. So because of the formation of these scums or precipitates, water does not lather with soap. So the property of water to form an insoluble curd with soap instead of lather. So in other words, it is a soap destroying property due to the presence of bicarbonate, sulfates, and chlorides of calcium and magnesium. Then hardness is of again two types, that is temporary hardness and permanent hardness. Temporary hardness, it is due to the presence of bicarbonates of calcium and magnesium and can be removed by boiling. Then permanent hardness, it is due to the presence of sulfates, nitrates and chlorides of calcium and magnesium. Then for temporary hardness, it can be removed by boiling and by addition of lime, whereas permanent hardness, addition of lime, soda, and then ion exchange, then zeolite process, all these have to be done for removing the permanent hardness. And then coming to its units of hardness, hardness is units are ppm, that is parts per million, nothing but it is the parts of calcium carbonate equivalent present per 10 power 6. It's not 106, so it's wrongly written here. It's 10 power 6 parts of water, that is 1 ppm. Okay, is equal to 1 part of calcium carbonate equivalents in 10 power 6 parts of water. Then milligrams per liter, number of milligrams of calcium carbonate equivalents, hardness present per liter of water. Then Clark's degree, that is The number of grains of calcium carbonate equivalents present per gallon of water. Then degree French, um, 10 power 5 parts of water. Okay, and then milli equivalents per liter, number of milli equivalents of hardness present per liter. And the main calculation part is 1 ppm is equal to 1 mg per liter is equal to zero point 0.1 degree French, that is equal to 0.07 degree Clark, that is equal to 0.02 milliequivalent per liter. This is the units of hardness. Then how hardness is expressed? So hardness is always expressed in terms of calcium carbonate equivalents. Why? Because its molecular weight is 100 and it is the most precipitated out of water treatments. Okay, so whatever water treatment you do, calcium salts precipitate out as calcium carbonate. That is why we express hardness in terms of calcium carbonate equivalents. So please remember that for hardness expression we use calcium carbonate equivalents, and then for units it is parts per million or mg per liter. So this is about our, that is, conducting polymers and introduction of water. Thank you.